Okay, so this is integration by parts. This is our third antiderivative technique that we're going to do. So far we know how to do the power rule for antiderivatives. We know how to undo a chain rule, which is using a substitution, or U substitution as it's most commonly called. This one is integration by parts. This is our third technique for antiderivatives. This is going to undo the product rule for derivatives. So we're going to do this in probably two videos. I'm going to try and keep each video to about 20 minutes or less. So hopefully it won't be too long. And it'll be a little bit easier to download these things when it comes time to it. Or upload them, I guess, to YouTube. Okay, so here we go. Product rule for derivatives. So if we're going to undo the product rule, let's go back and revisit what the product rule is. So the product rule for derivatives says, if I take the derivative of some product of functions, so f of x, g of x. Order doesn't really matter, but I'm just going to go with f and g. That's going to be f prime of x, g of x, plus g prime of x, f of x, right? Derivative of the first times the second plus derivative of the second times the first. Some of you may flip the order of these two, and that's fine. It doesn't matter because it is a product rule. As long as you have one derivative with the non-derivative and then the other derivative with the other non-derivative, it doesn't matter with the product rule. So logically, what we should think is, if the derivative of this product is this, if I were to go ahead and integrate f prime of x, g of x, plus g prime of x, f of x, we should end up right back where we started from. We should get some kind of f of x, g of x. Of course, since we're going backwards, and this is an indefinite integral, we've got a plus c. So using properties of integration, we can actually rewrite this integral right here. Oops, I did forget a dx here, didn't I? Bad notation. Okay, so in order to show what I want to show, we can use properties of integrals here. We're going to rewrite this integral right here. If I rewrite the integral, one of the properties says if I'm adding, I can separate the integrals into two different integrals. So we're going to have the integral of f prime of x, g of x, dx, plus the integral of g prime of x, f of x, dx. And again, if I separate these two, it's really the same as taking this integral, so it should end up with f of x, g of x, and again, plus some constant c. So if we algebraically rearrange this line right here, which we can do, ultimately what I'm going to end up solving for is, let's do red, is this guy right here. It doesn't really matter. Technically, we could algebraically solve for this one right here, but the most common form that we're going to use is this one. So we're going to algebraically solve for this. So if I want to algebraically solve for this, it means I need to subtract that integral to both sides of this equation. So we'll go ahead and do that. And when I do this, I am going to actually switch the order of this just to put it in a more common form that we're used to seeing. So, and you know, you'll see what I mean. So if I'm going to solve for this integral right here, which is right here, an integral of f of x g prime, so you can see I just switched the f and the g prime order here, doesn't matter, is going to equal, well, it's going to equal this thing right here, f of x, g of x. I'm going to hold off on the plus c for now, it can go at the very end, minus all of this, minus the integral, and again, I'm going to change the order. I'm going to put g first, and then f prime of x, dx. And then, of course, some plus c out here. This is the most common form that we're going to use. Now, what does all this mean? Because this is really kind of a cumbersome formula to write. So what we've done is we've taken the formula and we're going to do a little bit of substitution of some variables here just to make it a little bit easier. And we commonly use u's and v's, which is not the best combination because the way I write them, they look very similar. So I'll do my best to make sure that you guys can tell the difference. But u is going to be f of x, v is going to be g of x. So literally when I rewrite this, this is going to be u, this is going to be v, minus the integral. This right here again is v. Now this is f prime of x dx, which is really just the derivative of this. So this is going to be, this whole thing right here is going to be du. See, that looks too much like a v. Du. There we go. So what this is really saying is this integral right here, again, f of x is u, g prime of x is really dv, because it's the derivative of this, which is dv. So this is the integral of u dv, which is actually a product. It's a product of f of x times g prime of x. It is the product of two things. Don't let the fact that this is a g prime fool you. This is still going to be a product of two functions. It's just it happens to be that this one happens to be a derivative of something, which is fine. It's still the product rule of two functions. So when we undo it, undoing the product rule here is going to be uv minus the integral of v du. And then, of course, we'll have a plus c out here if we don't have bounds. All right, and here it is down here at the bottom. Integral of uv equals, integral of u dv equals uv minus the integral of v du. This is something you will absolutely have to memorize, and for whatever reason, most people don't seem to have a hard time memorizing that formula. The only difference is that if we have bounds, so a to b, it extends to having bounds on both of these, and you'll see why it's written like this when we go through some of the problems. So this is called integration by parts. So let's go ahead and do a couple examples, and hopefully you'll start to pick up what's going on here. All right, I have the integral of x sine of x dx. Standard u substitution would not work here because if you let u be the composited piece x, if I take du, it's dx, it's not going to get rid of this x over here, so we'd have two variables left over. Standard u substitution doesn't work. This is a product of two things, x times sine of x, so therefore you can't just take an antiderivative. Remember, we cannot split integrals through multiplication, but what we can do is we can do this integration by parts. So let's see what happens. So I'm going to let u equal x. I'm going to let dv equals sine of x. That doesn't look good. I'm going to let dv equals sine of x dx. There we go. Okay, so this is u right here. That's your f of x. This is sine of x dx. That's my dv. That's basically your g prime of x. So that's what I'm calling these two things right here from our formula. Well, in order to solve this, I don't just need u and dv. I'm going to also need du, and I'm going to need v. So how do I get du from u? Well, you take a derivative. So du is going to be 1 dx. So du in this case just equals dx. V is going to come from this one, but this is dv, which is a derivative, so to get v, I take an antiderivative, and when I take the antiderivative of sine of x, I get negative cosine x. And some of you may ask, well, where did the dx go? Well, if I took the antiderivative, technically, if I had divided both sides by dx, I would have gotten a dv over dx equals sine of x, and then take the antiderivative of this, you get v equals negative cosine x. And likewise, and I'm not going to write it down, likewise, this right over here, if I took the derivative, would technically be du over dx equals 1, and then you would multiply the dx over, and you would get du equals dx. Hopefully that makes sense. Okay, so the pattern says if I want to find this integral, it is u times v minus the integral of v du. And it's okay if you got to keep going back and referencing that for right now. You'll get it eventually. So if I go ahead and write this down, let's make this pen thinner. This is going to be, this thing equals uv, which is x times negative cosine x, so negative x cosine x, minus the integral of v times du. Well, that's going to be negative cosine x dx. Okay, so far that's what this thing equals. Well, I still have an integral here that I have to evaluate, but I've gotten it to a point now where I can actually take the antiderivative and use the fundamental theorem here to evaluate this integral. So I've got negative x cosine x, that doesn't change. This is going to become, let's see, the antiderivative of negative cosine is negative sine, but that negative out here is going to make that positive, so we get plus sine of x, and then of course a plus c on the end. So this is the integral of x sine x dx. And if you were to go ahead and take the derivative of this, which you can see definitely has a product in it, if you take the derivative of this, which has a product rule, you're going to, after simplification, you'll end up right back at this x sine of x. All right, so a couple of logical questions. One would be, because I just arbitrarily came up with these values, how in the heck did I decide what was u, what was dv? How do I know? Because it's not necessarily in the order that it's written here. You know, this could have said sine of x times x, then dx. So we got to come up with the idea, how do I decide on u? How do I decide on dv? Well, there's a little acronym that, this is the way I learned it growing up. I've seen some other forms of this, but it all has exactly the same basic order. This acronym right here tells you what you're going to select for u. So this acronym, and I'll write the pieces for it, this tells us the order to select our u. Ah, there we go. This tells us the order to select our u. So, and again, I'll go with that when we hit this next problem. So this is the general order that we're going to select these things in. The L stands for log functions. So if you happen to have a log function in your integral, it's the very first thing that you would look for, and if you do, that's going to be your u value. If you don't have a log, then you would look for inverse trig functions. That would be the next thing that you would look for u. If you don't have one of those two things, the next one you're going to look for is a power function. Okay, not necessarily a polynomial, but a power function could be x to the 1/2, x to the 3/4, something like that. Not an exponential, but a power function. Variable in the base raised to some kind of an exponent. It does not have to be a whole number, so it doesn't have to be a polynomial. E then stands for exponential. So if we don't have any of the rest of these, we'd look for that one exponential. If we have an exponential function, it would be our u. And then the last thing we would look for is just standard trig functions. So LIPET, L-I-P-E-T, it's the acronym that we use. So hopefully you guys will remember eventually that LIPET is the way to think about what is going to be your u value. So if we look at our second example here, I have the integral of the natural log of x dx. Well, I only have one function, but it happens to be a log, which fits our very first criteria. It's the first thing I would look for. So if that's the case, this is going to be ln of x is a log, so this is going to be our u, ln of x. dv, when you come up with your u, is everything that's left over. Well, if I get rid of the natural log of x, the only thing I have left is dx. And then we're always going to need to find du and v to do this. So du is the derivative of natural log of x, that is 1 over x dx. And then the antiderivative here, really technically this is 1 dx, so the antiderivative of 1 is just x. And then we've got our information here, and we can go with our pattern, which says it's uv minus the integral of v du. So this integral right here is equivalent to uv, which is x ln x, minus the integral of v, which is x times du. X times 1 over x dx. Well, this one's really nice because x times 1 over x is just 1. So really, this is x ln x minus, this is the antiderivative of 1, so that's just x plus c. That is the integral of the natural log of x dx. And again, you can see how they started off with a product rule within here. There is something else here, but you started off with a product rule, and we're undoing that. So if you took the derivative of this, you would basically, after simplification, end up with natural log of x. Okay, so again, the key takeaway on this one is the u value is going to be determined by this acronym LIPET. L-I-P-E-T, log, inverse trig, power, exponential, and then regular trig. That'll determine your u. Okay, this will probably be the last example, and then we'll come back and finish it up. So in this case, I've got t squared e to the t dt. So if you look at these two functions right here, t squared is a power function. E to the t is an exponential. According to our acronym LIPET, L-I-P-E-T, power functions come first. So that means my u is t squared. That means dv is everything else that's left. So it's e to the t dt. Okay, and then we're going to need to find du, which is the derivative of this. So that's 2t dt. And then we have to find the antiderivative of this one, e to the t. Fortunately, the antiderivative is e to the t. That was nice and easy. So let's go ahead and follow our pattern, which says u times v minus the integral of v du. So this thing equals u times v, which is t squared e to the t, minus the integral of v du, so that's e to the t times 2t, so 2t e to the t dt. The problem is now I'm actually left with another one of these things which I cannot integrate yet. So what that means is, yes, we have to do it again. So we're going to have to perform another integration by parts. This is not that uncommon. So this piece stays the way it is. We're just going to take this and do another integration by parts. So u, in this case, again, 2t is a power function, e to the t is exponential, so u is 2t, which makes dv everything else that's left over, which is e to the t dt. So the derivative of u is 2 dt. Antiderivative here of dv, to get back to v, is v equals e to the t. And then once again, we're going to go ahead and do our little pattern. U v minus the integral of v du. Okay, this stuff stays the same. It hasn't changed. It's still part of the original integral. We just had to do another integration by parts to fix this part. So this is still going to be t squared e to the t minus. Now, I've got this entire integral which I have to do this for. So uv, 2t e to the t, minus the integral of v, which is e to the t, du, which is 2 dt. So 2 e to the t dt. Now hopefully what you can see is that this is now something where I can actually just go ahead and take the integral. Because I can integrate 2 e to the t. Technically you could pull 2 to the front, and then you're just taking antiderivative of e to the t, which of course is e to the t. So we're pretty much done now. So all we have to do is, let's rewrite this, t squared e to the t distribute the negative, so minus 2t e to the t, distribute the negative to here gives me plus, and then the antiderivative of 2e to the t is just 2e to the t plus c. And this actually is multiple products. But again, what we did was we undid a product rule right here, because this right here was a product rule. There's a product here, and then that one's just 2e to the t. But we had product rule, you take the derivative of all this, you end up with t squared e to the t dt. Alright, so we're going to come back with a second video and finish this thing out. I'm actually going to show you, because, I mean, yes, this wasn't horrible to do when you have to do two of these, but if you can imagine maybe if this t squared was t to the 7th power, that you might have to do 7 integration by parts. That's a lot. There's a shortcut to doing a problem that is of this nature right here, and I'm going to show that to you guys in the first problem, the next one, and then we'll do a couple others that are pretty standard type of integration by parts.